Okay, what's up, guys? So we are going to be doing rate equations the day before the exam. My exam is tomorrow. Some of the students that do watch my videos also have the exam tomorrow. So good luck, guys. This is going to be on rate equations. Hopefully this video will serve you useful. My name is Yaz. If you didn't know that, we'll get to know. All right. So question one states this question involves the use of kinetic data to deduce the order of a reaction. So basically, to determine order, this is something you just have to know. To determine order, you need some sort of table, some sort of thing. You can't just determine it by looking at a reaction. You need data, you need numbers, things like that, okay? And when we're looking at something like this, to determine the order, we have to look at each experiment and which kind of concentration has an effect. So if we look over here, hopefully my microphone's on. If we look over here, we have the initial concentration of A, the initial concentration of B, and then we have the mole initial rate. So what we do here when we're presented with a table of this and we're told to deduce the rate expression for each reaction between A and B, for the reaction between A and B, what we do is we find out how much is multiplied. So if we look over here, first, let's look from experiment 1 to 2. I always like to put experiment 1 to 2 just to show that I can deduce which order. So if you look at 1 to 2, we see that with A, it's times by 3. Now if we look over here, now if you put that in a calculator, you'll notice that this is times by 9, okay? However, the concentration of B has not changed, so this is times by 1. Okay, so the concentration of B has not changed, but then because of A changing, the initial rate has times by 9. What does that tell us? Well, from this we can determine that A has tripled in concentration, which caused the initial rate to times by 9. And if we know powers, we would know that 3 squared is equal to 9. So therefore, A has second order. And now we look for B. So we found out what A is, right? We found one change. So this has changed, and therefore this caused the concentration, the initial rate to change. So we know that A is that, so we can remove all the data. And now we look through what the order of B is. So if you look at B, this has not changed, so this has remained the same, and this has times by 3, this has times by 2, however, this has halved, right? Now the thing is, when we're given tables like this, what you have to do is kind of like spotting the pattern, okay? So this has times by 2. Now naturally, if this had no effect, if it was order 0, okay, and order 0 basically means anything to the power of 0 would just be 1. That means completely no effect, okay? If this was order 0, then technically this would be times 4, right? So if we do this divided by that, we should get 4, but we don't. We get it doubled, okay? This has halved, right? And this has doubled. So technically this should be 2 squared, right? If it was order 0. But it's not 2 squared. It's only 2. So this shows that B has an effect. It's not second order, right? Because it hasn't really made a change over here. So it's not 0 order. So B must be first order. So we write down experiment 2 to 3 shows B is first order, as when it halved, it had the had an effect to the concentration or the initial rate. I'll just put initial rate, don't want to confuse you. Okay, so that's 3 marks when you work that out. Now we move on to the next question. So next question states, so we're given another table, and then this time we don't really have a initial rate over here. We are given an equation though, so we don't need to work out the orders, because the orders is 2 and 1. Now, when we're doing the orders, by the way, when we're putting them in our formula, 1 does not show, 2 shows, and then if it's order 0, it would just disappear, because order 0 is just 1, and anything times by 1 is the same thing, so we don't really show it. And that's how it works. So what we do, we're trying to find this. It's telling us use the data from experiment 4 to calculate a value for the rate constant, K, at this temperature, deduce the units. So far it's only asking us for what K is. And then after that, it's going to ask us for calculate a value for the initial rate in experiment 5. This is experiment 5, and it's asking us to calculate this. Okay? So first things first, we've got to find out what K is. And now, to find out what K is, well, we know that the initial rate is 7.2 times 10 to the negative 4. And we don't know K, but we know C. 1.9 times 10 to the negative 2. And then we times that by, we'd put the power of 2 on that. And we also have D, which is 3.5 times 10 to the negative 2. Okay? That's our equation. So we know what the initial is, and we got C and D, and we put it in the respective order. So this is squared, and this is to the power of 1, so it's just itself. And now we rearrange to find K, making K basically by itself. Okay, and how we do that is we do 7.2 times 10 to the negative 4, and basically we drag all of that and put it over there, under it. Okay, so what we do then is 1.9 times 10 to the negative 2, 3.5 times 10 to the negative 2. Now keep in mind, I know I haven't mentioned this, but this is really important. When you're putting an equation, square brackets means concentration. Okay, so don't be putting any circular arch-like brackets, because that wouldn't count and you may lose a mark for that. Anyways, so we get this, and that is equal to K. So we work it out, and we get an answer of 5.57. So I looked at the other answer. We got 57. Okay, now if you look at this is in seconds, this is in moles per decimeter, this is in moles per decimeter. So as safety, I'd also like to put the units and kind of work it out like that. So we got per second over here, and then we got, if we times everything together, we get moles. So that should be squared, by the way. Moles squared. So that should be moles to the power 3 decimeter minus 9. And then what we are left with is, if we cancel the bottom with the top, we are left with mole per negative 2, because it's on the bottom, decimeter minus 6 per second minus 1. Okay? So the seconds is not affected. So calculate a value for the initial rate in experiment 5. So now that we know what K is, we know how to calculate the rate. So this time, instead of finding out what K is, we find out what the to be calculated part is. And that is 57 times 3.6 times 10 to the negative 2. Respecting that equation, we put a squared on that. And then we do 5.4 times 10 to the negative 2, which gives us 3.99 times 10 to the negative 3, which would be our answer. Okay, next part. So this one is kind of an understanding part of it. So you have to understand what is K, what is rate, what is the concentration about, to really put this into words. So for a reaction to occur, what must happen is particles must have enough activation energy, have greater than or equal to activation energy to react and form a product. Now, rate of reactions is basically finding out how fast a product is formed. Okay, so when we're looking at this, for example, we're working out how fast, you know, it how much time it takes for a product to be formed. So over here, explain why quantifiably, quantitatively, why doubling the temperature has a much greater effect than on the rate than doubling the concentration. Doubling the temperature causes more molecules to have activation energy greater than the minimum. Okay, so increasing temperature allows molecules to gain activation energy greater than or equal to, so energy greater than or equal to activation energy. And activation energy is basically the minimum energy required for collisions to successfully form a kind of product. Okay, so this is my first point. My second point would be doubling the concentration would add more particles in a volume. However, this does not change activation energy. So what you're doing is basically you're doubling the concentration, but the problem is the concentration wouldn't have as strong as an effect. Sure, it will have an effect. Particles are more likely to collide, but it won't have as a great as effect because they won't have the minimum energy required. Whereas temperature causes most molecules to achieve that minimum energy required to successfully collide and form a product. Therefore, increasing temp has greater effect because more particles successfully collide, and to say, to form a reaction. So now we got part E, which looks a little daunting, I'll admit. When I was doing this paper, I thought this was slightly daunting, but to be honest, there's two ways to go about it. One, you can rearrange this from that, or two, you can memorize a kind of equation to rearrange it already. So what you have to do is you have to rearrange that, without the minus of course, that, and make it equal to ... equal to all of this. Okay? Or you can memorize it, which is, I would say, I don't know, I would memorize it in my opinion, because I'm not very good at rearranging and it's a bit risky. So you can memorize it and just do this. No shame in both. You can make a nice mnemonic with that. So this would be your equation, and then you basically plug everything in. So we get activation energy, activation energy is 8.31 times 300, and then that is a ln 2.57 times 10 to the 10. By the way, we divide that all by 1,000 don't want to forget that. And then that is minus ln and ln 6.51 times 10 to the negative 3, which would give you 72.3. If you put that correct, that's what it should give you. Okay, so that's your activation energy. You could say this is kilojoules per mole. Okay, so that's your answer. So we go on to the next part. This is our question 2, and question 2 we're given a table. Automatically I kind of think when I see a table, I'm thinking orders, I'm thinking rates, I'm thinking concentrations. You know what I mean? So this is kind of something you just kind of, it comes with practice in it. It's slightly daunting at first, but it comes with practice. Anyways, so what we see over here is same thing. This doubles, so this times 2. And this stays the same, so it's times 1. Okay? And then what we see over here is this doubles as well. So this is times 2. Okay? So what happens is this doubled, which caused the concentration to double. Okay? So I'm thinking maybe order 1. Okay? But let's carry on. Now, when this doubled, okay, what happened is this times by 8, however, this also doubled by 2. So, if we assume this is first order, because it kind of shows that it's first order, this doubled, and that doubled, and 2 equals 2, which is 1 equals 1, which shows this is first order. So A is first order. So we can calmly assume that when this doubles, this is basically 2 to the power 1. And when this is equal to times by 8, so this is equal to 8, right? This, what will happen is, this would have to be to the power of 2, right? Because, this should be a times. This would have to be, because you're timesing the concentrations together with a constant to find this, right? So we can safely assume this is first order, okay? And because of that, and it's because it's times by 8, we can also safely assume this is second order, because if it's first order, we wouldn't get that. We would get 2. And if this is 0 order, we would just get 2. If it was first order, we would get 4. And if it was 0 order, we would get 2, right? We would get, 1, we would get 2, okay? So safely we can assume this is second order, because second order is 4, okay? And 2 times 4 is equal to 8. So we can safely assume that B is second order. Sorry for my scrambling. It's just my mind's going on all over the place. Okay, so we get part B now. Okay, and the following data obtained in a second series of experiments on the rate of reaction between compounds C and D are at a constant temperature. So this is another table, and we got another kind of to be calculated. Okay, and we're also given an equation. Cool. I'm already thinking find K and find rate already, because we don't know K, we don't know rate for this one, so it's probably going to tell us that. Boom. Yes, it is. So find the values of K. Now, unfortunately, the equation's over here, so let's just move it over here. Rate equals K, what was it, C squared? Yeah, C squared, and then D. Okay, and so what do we do with this one? So we got C, and we got D, and we got rate. Again, 9.3, what was it, times 10 to the negative 5. Oh, my pen's gone. Negative 5 is equal to K CD, so 0.75 squared times D, 1.5. That remains the same, and we respect the equation by making it squared. 1 second.